Okay, welcome to today's class. In the previous lesson, we were discussing about engineering properties of engineering materials, and we discussed quite a number of them. We have mechanical properties of engineering materials, we have physical properties, among other properties, and we dwell majorly on mechanical properties of engineering materials and physical properties. And we said some of the mechanical properties of engineering materials. We have strength of the material, we have ductility, we have plasticity, we have brittleness of the material, we have malleability, and we defined all this. I'm expecting that you still remember all that we learned in the previous lesson. Okay, before we start this lesson today, I would like you to make sure that you've marked the register before we continue, because the lesson might come to an end before you guys have marked the register, and the system will automatically indicate that you did not attend this class. So it's always important to start the lesson by marking the register. Welcome. For today's lesson, we are going to study about the common structures of crystal structures of engineering materials. You realize that most materials are crystalline in nature. Every material, we have metals, wood, soil. All these are made up of crystals, and we have some common crystal structures. So for today's lesson, the objective of the lesson will be to discuss or to define what is a crystalline state in materials, and also name and explain some common uh, crystal structures of engineering materials. So a crystal structure consists of atoms arranged in a pattern that repeats periodically in a three-dimensional lattice. Geometric lattice. Geometric lattice. For metals, in metals and in many other solids, the atoms are arranged in irregular arrays called crystals. A crystal structure consists of atoms arranged in a pattern that repeats periodically in a three-dimensional geometric lattice. The forces of chemical bonding causes this repetition. This is repeated This is a repeated pattern which controls properties like whatever we discussed in the previous lesson, like strength of the material, we have ductility of the material, density of the materials, among other properties like conductivity of the material, property of material or of property of conducting or transmitting it, electricity, etc., and even the shape of the material, that is, on the physical properties of the material. In general, there are three common crystal structures, basic crystal patterns associated with metals. The first one is the body-centered cubic structure. We have a face-centered cubic structure, and you have uh, hexagonal packed, hexagonal cross-packed structure. And I'm going to give you some of the definition of what do we mean when we say body-centered cubic structure, basically abbreviated as BCC. And you see a term BCC, just know that it means the body-centered cubic structure. In body-centered cubic structure, arrangement of atoms, the unit cell consists of 8 atoms. A cube has 8 sides, we have 8 corners. So in every corner of the cube, we have an atom, and at the center of the cube, we have another atom. So we are saying the arrangement of atoms on the units consists of 8 atoms at the corners of the cube and 1 atom at the center of the cube. For the face-centered cubic structure, in face-centered cubic structure, or rather FCC, arrangement of atoms, the unit cell consists of 8 atoms at the corners of the cube and 1 atom at the center of each face of the cube. We all know that a cube has about how many faces do we have in a cube? We have 6, or 1, 2, 3, 4, and the top and the bottom one, we have 6 faces. So in every face, the cross section, or rather the intersection of the of the diagonals faces of the cube, we have an atom in between. An atom in between. And the last one is hexagonal cross-packed crystal structure. In hexagonal cross-packed crystal structure, or rather abbreviated as HCP, arrangement of atoms, the unit cell consists of 3 layers of atoms, the top and the bottom layers containing 6 atoms at the corners of the hexagon, and 1 atom. Yes, the top layer contains 6 atoms at the corners of the atom and 1 atom at the center of each hexagon. We all know an hexagon has 6 sides. A hexagon is a six-sided figure, so we have 6 corners in an hexagon. So we have an atom in each corner of the atom of the hexagon, and we have another atom at the center, at the intersection of the diagonals of the hexagon. The middle layer contains 3 atoms nested between the atoms of the top and the bottom layers, hence the name cross-packed. So we have another 3 atoms at the center, in between the top layer and the bottom layer of the hexagon. I'm going to share with you an image showing the structures. They will show you how these structures are appeared, or how they are drawn, or how they appear, or the arrangement of the atoms, how they are arranged. So I'm going to go to and give you some of the examples of the metals that contain these structures that we just learned, that is BCC, FCC, and HCP. For BCC, here are some of the metals that contain this kind of structure. We have ferritic, or rather ferrite. We have chromium, they contain this structure. We have vanadium, molybdenum, and tungsten. I'm hoping that you are taking some small notes. These metals possess high strength and low ductility. For metals containing FCC, or face-centered cubic structures, in clad austenite, we have aluminium, we have copper, we have lead, silver, gold, nickel, platinum, and thorium. This metal possesses low strength and high ductility. Metals containing the HCP in clad, rather hexagonal cross-packed, include beryllium, we have magnesium, we have zinc, we have cadmium, cobalt, gallium, zirconium. HCP metals are not as ductile as for the FCC. So that marks the end of the content today. I'm just going to do a quick recap of whatever we've learned today. We learned about the crystal structures of materials, and we said we have 3 common basic crystal structures of material. We have face-centered cubic structures of material. We have body-centered cubic structures of material. We have hexagonal cross-packed structures in materials, and we also discussed about examples of materials that contain these structures. For metals containing the BCC structures, we said we have metals like vanadium, we have chromium, molybdenum, tungsten, and we also said that these metals contain high strength and low ductility. For metals containing the FCC, or face-centered structures, we have examples like aluminium, copper, lead, silver, among others. We also say that this metal possesses low strength and high ductility. They are very ductile. For metals containing the HCP, or rather hexagonal cross-packed structures, they include beryllium, magnesium, zinc, cadmium, cobalt, thallium. We also said that these metals, or metals that contain HCP structures, are not as ductile as for the FCC metals. I'm going to share with you a video, or rather an image, showing how these structures are drawn, because this is one of the common questions that always comes in exam. You should be able to explain when you are asked to explain, or rather draw a structure containing BCC or FCC, you should be able to do that with a lot of ease. So make sure that you download the content that I'm going to share with you after this class in your LMS. Thank you.